Hello, everyone. Today, I'd like to share another open-source tendon-driven dexterous hand, the RUKA hand. Its size is comparable to a human hand, with 5 fingers, 15 degrees of freedom, and powered by 11 motors. The main body and parts are primarily 3D printed, and the total cost is around 1,300 US dollars. As always, I put the open-source link in the video description. Don't forget to like, bookmark, and subscribe if you find this useful. Alright, let's get into the mechanical design of RUKA. All of its motors are mounted in the forearm, and the hand uses a tendon-driven mechanism, where nylon lines running over pulleys transmit power to the fingers. Both the fingers and the palm are 3D printed with PLA, while the fingertips and the palm surface are covered with 3D printed TPU pads to increase friction and improve gripping ability. The thumb has 3 degrees of freedom, each driven by its own motor, extension and flexion, abduction and adduction, and opposition. The other 4 fingers also have 3 degrees of freedom each, but the 2 distal joints share one motor, while the proximal joint has its own dedicated motor. Finger extension is provided passively through 3 pre-stretched springs mounted on the back of each finger. As for actuators, RUKA uses dynamixel motors. The thumb is powered by 3 XM430W210T units, while each of the other fingers is driven by 2 XL330M288T motors, which provide lower torque compared to the thumb. Now that we've gone over the mechanical design, the big questions are, how dexterous is RUKA, and how much load can it handle? Let's take a look. In terms of dexterity, RUKA was evaluated using standardized benchmarks. One of them is the Kaplan-G test, which originally comes from medicine and is used to assess thumb mobility and opposition in patients with impaired hand function. The scoring starts at 1 when the thumb can touch the second joint of the index finger and gradually increases as the thumb touches 10 specific points across the hand, with a maximum score of 10 when it can reach the palm crease below the little finger. This test has since been adopted for robotic hands, and RUKA achieved a maximum score of 10, showing strong thumb dexterity and opposition capability. RUKA was also tested with the grasp taxonomy, a system that classifies human grasp types into 33 categories, including power grasps, precision grasps, and intermediate forms. RUKA successfully demonstrated 29 out of the 33 grasp types, which highlights its versatility. Moving on to load capacity, RUKA's fingertip pinch force reaches 2.7 newtons, and its maximum grasping load goes up to 6 kilograms. At the proximal MCP joint, the load capacity is about 16 newtons, while the combined capacity at the distal PIP and DIP joints reaches as high as 33 newtons. Finally, in durability testing, RUKA was able to operate continuously for over 20 hours, while still maintaining good motor accuracy, thanks largely to the heat dissipation of its motor housings. Next, let's take a look at RUKA's control system. One of the main challenges with tendon-driven hands is that the relationship between motor positions and joint angles is highly complex and difficult to model. This complexity comes from issues like tendon slack after repeated use and slippage on the pulleys, both of which introduce hysteresis into the system. RUKA tackles this by building a data-driven model. The research team mounted a Manus motion capture glove directly onto the RUKA hand. By driving each joint of the robotic hand, they simultaneously collected its posture data and the corresponding motor angle data. Using this dataset, they trained 2 neural networks, an LSTM and an MLP, to map fingertip positions and joint angles to motor angles, effectively serving as an open-loop controller. With this approach, once a target posture is specified, the model can directly compute the required motor angles. As a result, the average error at the thumb's tip across 3 spatial directions was reduced to just 2 to 8 millimeters. The research team also explored teleoperation with RUKA, performing various grasping actions and even more complex arm-hand coordination tasks. In this setup, a human operator wears a Manus glove to control the robotic hand, while our RUKA markers are used to track the arm's posture. But they went a step further, into one of the most exciting emerging directions in robotics and computer vision, training robots directly from human demonstration videos. To test RUKA's ability in this area, they adopted a framework called HUDOR. So, what is HUDOR?
Close the door!
And no, it's not hold the door. Its full name is human to robot dexterity via object-oriented rewards. Here's how it works. Udor takes human demonstration videos and converts them into open-loop replay trajectories for the robot. Then it refines these trajectories by learning a residual policy, with the reward function computed by comparing the trajectories of the object's center of mass during the human and robot demonstrations. With this approach, RUKA can learn to perform complex tasks without teleoperation, using nothing more than a human demonstration video. For example, rolling a cube or grasping and placing a piece of bread. To sum up, the design of RUKA is relatively simple. It doesn't have tactile sensors, tendon tensioning mechanisms, or active abduction control for the fingers. But through this streamlined design, it manages to combine high dexterity with high load capacity. With data-driven modeling, it achieves effective posture control, and with teleoperation and imitation learning, it can handle complex manipulation tasks. If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.